Hey, good morning, students. What we're going to cover today is interference and resonance. What you're going to learn is about what happens when waves overlap. They tend to either build up or cancel out, depending on how they're matched up. This leads to a whole bunch of interesting different effects. An important one is resonance, the idea that an object can kind of like vibrate at a natural frequency, but it applies to a whole lot more than just sound waves, too. So, we're going to look through a whole bunch of different examples of this. You guys are also going to be able to distinguish between a simple and a complicated waveform. And we're going to get a little practice graphing some waves too. You guys will have a handout to practice with later today too and some Kahoot. Go ahead and pause the video for a sec and check out which vocab words you feel good about, which ones you might want to come to office hours and ask more about or else look up. We've covered the green ones. Blue ones are coming up here soon. All right, we'll keep going. So the idea is you can have two waves of the same type in the same space at the same time. For example, you could send in a wave going this way, and you could send in a wave going this way, and obviously they're going to cross paths and meet. And the question is, what happens when they do that? So take a look. In this example right here, the waves are matched up exactly. When this one is facing up, this one is facing up. When this one is facing down, this one is facing down. If they overlap in that kind of arrangement, which is called in phase means they're matched up, then what you get is that the amplitude, how big the wave is, actually appears much bigger as a result of the two combining. So this is called constructive interference because we built up the wave. We're constructing a bigger amplitude. So when they're matched up, it tends to get bigger. Here's a counterexample. When this wave is up, this wave is down. When this wave has a negative value, this wave has a positive value. If we combine these, the two waves perfectly cancel out. We've destroyed the wave, so this is called destructive interference. In destructive interference, the waves are out of phase, they don't match up, and that makes them have a smaller overall amplitude. Now, this is like the either-or example. Nothing in real life is this clean. So what we're going to get is different combinations of constructive and destructive at the same time in most realistic examples. So over here, we've got a picture of like a ripple maker. Like let's say you're dropping rocks in a pond right here, and then you drop rocks in a pond right over here, and there's waves that spread out away from those rocks that you got dropped in the pond. Those waves are going to cross paths and overlap. Sometimes they'll do this like this and make a taller wave, constructive interference. Sometimes they'll overlap in a way where they're opposites, and they'll do destructive interference, and you'll just see a flat spot there, no wave at all. Here are some real-life examples of that picture. You can see there were two different sources of waves. What's really cool is you see the kind of like zigzaggy path right here. That is exactly what's happening in this picture. You can see the same thing here where these waves hit these gaps in the rocks. It diffracts, which means bends around a barrier and starts a new wave front system. And when they overlap, they're either overlapping in a way that builds up or cancels out. So we got a quick example of this coming up here. We can set this up and you guys can toy around with this. I linked this earlier. Okay, let's turn on some taps. They're dripping water. And you can see that there are places where they cancel out and also places where they build up even stronger. Like right here, along this axis, in between the two places where the drops hit, that will always be lined up. So that's always going to be constructive interference. This is as tall as the wave can get. This is as low as the wave can get. There's a biggest difference between top and bottom there. And so that's a high amplitude zone. Here, on the other hand, it's all kind of like exactly canceled out on this axis and on this axis here. So there you're going to have destructive interference. What you can do is you can change the spacing of these. And of course, this example has to do with waves in water, but we know that those aren't the only kinds of waves. So you can also do this with sound. And this is why if you go to a concert hall, it's been very carefully designed not to have dead spots. Is a dead spot the result of constructive or destructive interference? Hopefully you're thinking destructive. If you can't hear anything, it means they've canceled out. This is also how noise-canceling headphones work, which we'll talk about later, and why some things tend to buzz or hum at a certain pitch. Okay, well, cool. But that's not the only kind of wave. There's also light. you can actually get light waves to cancel out. And we're going to see some examples of this coming up just in a second here. If we had this in hands-on mode, I would actually have the gear to demonstrate this exact thing. It looks pretty cool. Sorry about that, guys. Alrighty, so let's keep going. So you may have seen, it rains on a parking lot and there was some oil there. You may have seen these cool shimmering oil slick images. Well, something really cool is happening. The incident light means the inbound light. So you can see this is a ray diagram. The ray shows the pathway that the light was following. So this is the direction the wave is headed. Incident means inbound. And it hits the oil slick and some of it reflects, but some of it keeps going through the oil layer and then gets to the water layer underneath the oil and reflects off that second layer instead, and then heads back out on that path. Now, the question is, which of these paths reflects right away or reflects later on has to travel farther? And hopefully you're thinking the one that bounced off the water traveled just a little bit farther than the one that bounced off the oil, and you'd be right. So then, here's a question. If we think of this as two different chunks of light, and they were lined up in phase here, are they still going to be in phase over here if one of them had to travel farther? And the answer is no, one of them would have fallen behind. If this one has fallen behind the other one by the correct amount, then it could be destructive. In this particular image, it's showing constructive. It's showing that they're lined up the same way, right? So if they got to your eye, you would definitely see whatever color light this represented. But if it had to travel just a little bit farther, this whole red squiggle would be scooted back. It would be offset by more, to the point where if it was destructive, you'd be missing that color. So what you're looking at right here in this oil slick is white light bouncing off, some water and oil. And occasionally a color goes missing when the thickness is the right distance to get the light half a wavelength behind. So you're actually seeing colors getting eliminated by destructive interference, and only the remaining colors that aren't eliminated are what show up to your eye. That's why these things look so cool. Same thing over here, you can tell that there's a whole bunch of different thicknesses, and it's changing thickness very gradually. Overall though, how thick or thin are we talking? Well, we are talking about, I'm just going to go 700 nanometers. We're going to pick some red light. I'm worried this is right left reflective. If I can fix that real quick. Let's see. I'm going to fix it. Hold on. Let's see. Well, shoot. That might not be something I can fix on the fly right now. Oh, wait, transform. There we go. You guys can read that hopefully now. Okay, so 700 nanometers. This is the wavelength of, for our symbol for wavelength is lambda, that weird Y symbol, upside down Y. That's the wavelength of red light, which is really times. And what we can do is we can use like a red laser, the other dealy bopper here. You can use like a red laser, and you can actually measure incredibly short distances by deliberately setting up whether this gets offset or not. And since this is based on interference, this thing is called an interferometer. Here's a picture of it in real life set up on an optical bench. What this can do is it can measure one, two, three, four, five, six. It can easily measure stuff that's that many meters across. And if you think, that's a centimeter. And if you think of a millimeter, which is the really tiny line on a ruler that's supposed to be hard to measure, that's a millimeter. So this is if you use the ruler. What's cool about this is using interference, you can measure a fraction of a red light wavelength, or you can use even a different colored laser if you want, and get even better if you use a blue or a green laser. So this is using an interferometer to measure really small things. Interferometer. Oh my goodness. Okay, I need some more coffee. All right, let's keep going. So, yeah, you can interfere not just sound waves or ocean waves, which you might have expected, water waves, but you can also interfere electromagnetic waves too, which is pretty awesome. So, what could you do with this technology? Well, one thing you could do is if you've got like a sound coming in, you could have a mic pickup on the outside of your headphones that would record that sound, and then it could play the exact opposite sound. And if it did that at exactly the right time, both the regular sound and the opposite sound would get to your ears simultaneously, and you'd hear absolutely nothing. So, like Bose noise canceling headphones, they're actually playing the opposite sounds that a mic pickup on the outside of the headphone is recording. You're doing it fast enough to get both to your ear at the exact same time. Another idea, jumping on a trampoline with friends. If you want to double bounce your friend, what you're doing is you're basically setting up a wave where, like, let's say you set the trampoline up like that, and also your friend sets the trampoline up like that. What's the result of those two waves put together? Well, I can see that this is kind of like lined up exactly, right? When this one's high, this one's high. In the middle of the trampoline, it's low. In the middle of the trampoline, it's low. So what you get is the result, which is something twice as low. And you've now stretched out the trampoline extra, and then if you let it go, of course, your friend goes rocketing through a tree. Hopefully doesn't break their arm. Okay, so you could do this on a trampoline. Same thing with pushing somebody on a swing. The concept is the same. If you push them at the right time, they'll cause constructive interference. They'll go higher. If you push them at the wrong time, you could possibly cause destructive interference and slow them down. Okay, now, weird idea. How do cell phones communicate? Well, what we're going to start out with is just electronic sine wave. It's really easy to manufacture. And you're going to have a nice, simple sine wave. But you might have heard that digital technology communicates using ones and zeros. So let's say that we for a zero. I'm going to label my graph weird like that because we're thinking digital now. So what I really want out of this, I don't want the thing that's up there. I might like want a 1 and a 0. The question is, how do I go from these sine waves, which are easy to build, to a square wave, which is much more kind of like weird shape? Well, here's what I can do. I can add multiple waves together. So I could take a second wave and I could overlap it. I'm not perfect, but doing okay for hand drawn here. This these and then here, this wave was too high. I pulled it down the other way. And here I perked up the corner. Here I perked up the opposite corner. Here I pulled down the center some. Here I perked up the opposite corner. What I can then do is, and I can add up multiple waves. I didn't really think about that one very much. Let's hope it's good. I can add up multiple waves to get them to cause it to be more and more square over time. So I can add up, number series stuff like, A of n and A of n minus 1. Yeah, that's where this comes in. You can use series of waves in a mathematical pattern to get pretty much any shape you want, including things like square waves. So by adding up more and more and more of these, you get closer and closer and closer to this like easy 1 and 0 digital pattern you need for cell phone communication or whatever other thing you wanted. And at some point, like it's close enough that you stop. Like you might only go to 8 waves. You don't have to go all the way to infinity waves to get it perfect. You don't have to get it perfectly to be able to communicate with digital info. All right, next up, we're going to look at some beats. What kind of beats? Rocking beats? No, definitely not block rocking beats. So let me search real quick. Beats, components. There we go. This is the thing we want. Check it out. You guys see how there are some patterns built into this? Actually, that's not a great. Oh, wait. Let's add the word physics to this. Maybe we'll do either comb or fence. Okay, this is a really good example. You guys know that the height of the wave is amplitude, and if we're talking about sound, that goes with loudness. So I don't know if you can see right here where my cursor is. This would be a really quiet part. This would be a really loud part. This would be a quiet part. This would be a loud part. How did we get this pattern? What we did is we had two separate other patterns that we're combining in either a constructive or destructive way. These two things aren't exactly the same wave, by the way. They're off by just a little bit in terms of their frequency. So with slightly different frequencies, they'll go in and out of sync, and that'll cause them to get louder or quieter over time. That's what physics calls beats. Let's see. I might come back to this later when I got a better example for you guys. I think by, let's see, Monday, I might also have something programmed to get you guys a live audio example you can listen to. And we can hopefully look at the waveform there. All right. So basically, beats is when something can go in and out of sync. And it'll cause an effect on the amplitude that matches up with the difference in the frequency of them. Okay, we talked about laser interferometers. Sweet, let's keep going. Now what we're going to do is we're going to try to draw some waves, and then we'll actually draw out the interference pattern they might make. So I'm just going to jot down this info on a piece of paper, and we'll switch back here. We've got a wavelength of 3 units. And an amplitude of 1. All right, so let's try to graph these things each separately. Okay, so I'm going to give this an amplitude of 1, 0, and minus 1. I like to put in some dotted lines just to help myself draw these correctly later. Remember, amplitude is from the center to the peak or the center to the trough. It's only half the overall height. So when this says amplitude of 1, it means we go from 0 up to 1, as well as from 0 down to negative 1. Next thing, I notice there's a least common multiple of 3 and 2. I'm going to space this graph out to 6. All right, and this wave has to repeat and start over completely every 3 units. I'm going to put a big dot right here. I know that it needs to go up and back down to center, and then down and back up to center every 3. Means it should cross the line right at 1.5 there. And then it's going to do the same thing again. It repeats every 3 units. So there we go. We got our first one drawn. Hey, rookie mistake. That would only be half the wavelength. Wavelength is the entire complete cycle. Okay, one other thing you can check here. From here to here, is it about 3? Yep, that does in fact look like 3 units. Same, 3 units. All right, so using the same amplitude. It's going to go up and down by 1, and then down and up by 2. There we go. By the way, with a smaller wavelength, would you get a higher or lower frequency? Assuming wave speeds were all the same. Hopefully you notice this wave is happening more often. Lower wavelengths go with higher frequency. Alrighty. So now the real question is, what does it look like if both of these waves combine? What I'm going to do is I'm going to make a new graph down here, up to 6 again. And I think that the amplitude could be as big as 2 possibly. Why do I think that? Well, one thing you can do is if you get perfect constructive interference, the amplitude of each wave separately can add up. And since each wave had an amplitude of 1, I might get an amplitude as big as 2. Now, what I'm going to do is at each x coordinate, I'm going to add up the y coordinates. So when x is 0, I've got 0 plus 0 equals 0. At about x is a half, I've got a little less than 1 and a little less than 1. Going to be a little less than 2. At x is 1, I've got about 1 and 0. At x is 1 1/2, I've got 0 and minus 1. And you guys can see that at each x coordinate, I'm just adding up the two y values to get the total. Now, is this going to be like a nice pretty shape? Probably not. This is going to be more of a complex waveform, and they can get pretty messy. Ooh, check it out. At 2 1/2, this one's up, and this one's down. That's destructive interference. We're going to get an amplitude of almost 0 there. And at 3, we've got a 0 and 0. And then what's really cool about this is this pattern is going to be symmetrical. So what's weird is we get that pattern. Does that look like the nice smooth sine wave cosine? Hey, by the way, hopefully you're thinking now, why did I choose to graph out to 6? That was the first place where both of these individual waves would be starting over at the same point, which means also that this is the first time that this pattern will be starting over. So it'll look like this pattern over and over again as these two things overlap. Okay, so hopefully you understand how to graph some waves by checking the amplitude and also making sure that it repeats a cycle each wavelength, assuming we're graphing over distances in meters. And then also, you know, the idea of interference is that at each location, the two y values add up. All we're doing is we're adding the one wave to the other wave to find the new total. And it can make a pretty messy shape. It does not have to be clean and pretty. So with that, let's keep going. All right, here's an example of what I was talking about. Don't freak out. This is not as scary as it looks. All it's saying is there's a sine wave, which is that kind of curve that keeps going up and down, and that it's adding up a whole bunch of them. This is an adding up sign. It's adding up a whole bunch of them from 1 all the way out to infinity. Well, technically, we're only going up to 25. And that after we add them up, it makes some y value, some shape. So this is just a function of how to add these things up. It looks scarier than it actually is. Here's the point, though. They chose the right math to get a whole bunch of sine waves to make this thing called a sawtooth pattern. You can get any pattern you want if you know the right math for it. Don't believe me? Go do some Japanese physics.
何メートルぐらいあるんですか？
深さが35メーターあります。
こちらは最先端の技術で水面にあらゆる波を再現できる特殊な水槽。海底油田などに使用するパイプに波や水圧がどのような影響を与えるかを調べるために使われます。そんなこの水槽はとんでもない能力を秘めているんです。
ちょっと面白い波を今日お見せしますので、これからどんな波が面白い波だろう期待してください。
わかりました。
それではお願いします。
面白い波とは一体何なのか、水面に注目。
わ、すごいね。ちょっと揺れてる。わ、水が歪んでる。
That's a lot of complicated waves overlapping. And ta-da! I made a heart out of water. It's amazing, right?
なんと水面に浮き出たのはハートのマーク。
Physics.
実際の海の波をいかに近づけて作るかっていう研究をしている。その過程でこういうことをできるようになった。
There's a couple of these in the world out
自
there
然
now.
界で起こりうるあらゆる波を再現できるこの装置。最新のテクノロジーがこうした摩訶不思議な現象を可能にしています。ハートマーク以外にも
Oh, check it out!
星型
If you add up enough waves, you can make any shape you want. This is for the nerds out there. This is a Mobius.
本当のマークまで。
こんなに複雑なことができるのはここだけど。
じゃあ唯一絵が描ける。
Curious, we'll go later Google what a Mobius is. It's pretty cool.
さすが日本だな。アピールしたらいいのに。
This is Japanese physics,
さら
right?
にこの研究所には完成したばかりの最新の水槽があるんだとか。 今回特別に見せてもらえることに。
That was the prototype. This is the finished one.
これどのくらいの広さなんですか？
長さで言って長い方が80メーター、幅が40メーター、深さが4.5メーターあります。
確かにオリンピックプールよりもでかいですね。
こちらは明日正式なお披露目を迎える世界最大の実験水槽。
Is that they're going to get
地震
multiple
の津
waves
波
that
や台
overlap
風
in
で
the
起こ
same
る波
space,
をより正確に
and by
再現し
controlling
シミュレ
the
ーションす
frequency
ること
and
ができます。
amplitude, or wavelength and
今
amplitude,
回
however you want
は
to think
そ
about
の
it.
お披露目に向け
By
たあ
following
る
a whole
デ
bunch
モ
of
ンスト
math,
レーシ
they
ョン
can
を
generate
初
any
公
shape they want
開。
through a combination of constructive and destructive interference. Interference is when the waves overlap and the amplitude of the result, the combined wave, the complex waveform, is adjusted.
マイクが走ってるのかと思った。
大きい。
すごいすごい。見て。うわすごい。怖いなんか。ちょっと怖い。
中に入ったらどうなる？
衝突するよ。
I think this is the orca. See the whale doing the whale tail splash thing? Pretty cool.
なんと水面から
Alright,
高さ4
in the
メートルに
PowerPoint
及
there
ぶ
is a
水
second link for
柱
another
が。
one of these videos where they go through a whole bunch more
これ
shapes.
は
If you guys would like
隕
to see
石
it,
が海面に落ち
just
た場
follow
合
that
に
link.
予想
It's
され
pretty
る
cool.
波
I
な
had a
の
good
だ
time
そう。
watching it. We are going to keep going though. So second link right here if you want. It's pretty good. I'll put it up in classroom too. And actually, what else would you use this for besides like a super cool surfing pool? Well, electronics. All of our electronics is using some kind of signal processing like this. Also, music, and then I'm not sure what else. Okay, so we talked about beats. Here comes kind of a more complicated idea, which is, let's say that the blue wave is the one that I send in. So the blue wave is the incident one traveling down the slinky or whatever. It gets to a point where it reflects and it comes back. The red wave is now the reflected wave. Okay? So we're sending an inbound wave and a return wave after it's reflected along the length of a slinky. Question is, what happens? And the answer is, it creates what appears to be a standing wave. They call it that because it looks like it's just standing still. It doesn't look like it's traveling both to the right and to the left. And this is actually really common. If you get a friend with a slinky and you start shaking the slinky together, you guys will always pretty much end up with a standing wave of some kind. You can make like the really simple one hump standing wave. You can make like the two hump standing wave. I wish I had my slinky on me. You can make more and more of these. And what's important about this is you see the red dots? That's where the amplitude isn't, moving the wave at all. Like nothing's moving here. That's called a node, a stationary point. And then right here, this is where it's moving as much as possible. This is where you get the most movement. That is the opposite. So that's called the antinode. So in a standing wave, you're going to get nodes and antinodes. Is a standing wave just one wave? No, it is an incident wave and a reflected wave interfering with each other to create the appearance that there's a bigger wave standing still. Okay. Here's an example of this. Let's see this thing get started, actually. We'll get it going on YouTube. Go full screen here. Okay, so you guys can see the incident waves coming in. You're going to get to this barrier and reflect off. And you can actually start to see the reflected wave making its progress on the way back based on the way it interacts with the other incident waves. So now we have a standing wave in the system. The reflected wave has made it all the way back. The incident wave has made it all the way down. The two things are overlapping, combining, and interfering to create nodes and antinodes. Can you guys see the point on this that's not moving, as well as the points on this that are moving the most possible? This is an example of a standing wave in water. You can do this with slinky, you can do this with light, you can do this with any kind of wave. All right, so cool example there. Let's keep going. Let's see, I feel like I'm missing one. All right, we'll come back and follow up on that later. Okay, in the meantime, a resonance. A resonance is the frequency at which an object naturally wants to vibrate. So this is important for musical instruments. If you have like a trumpet and you were playing it, oh dang, I left that at school too. You could basically set up inside the tube, just one note would come out. You can't play like multiple notes at the same time. Actually, you can, but it's complicated. And basically, because of the dimensions, a standing wave has to fit inside those dimensions. So, like if you have this end shut and this end shut, the wave inside there could be like that. It could be like that, but it has to be some pattern that matches the dimensions of the object. That's what creates a resonance. And what's cool about resonance is you can use constructive interference to maintain it and keep the amplitude high. Other frequencies will tend to die off. And yeah, this is a big deal in musical instruments. What I have here is images of a computer model drum head. And you can actually do this in real life with real drums too. Across the top, we have the simplest possible pattern. The outside is a boundary condition. That's the way the drum head is fixed in place against the wooden frame or metal frame or whatever. That part can't move. Since it can't move, would you call that a node or antinode? That is the node. And then the antinode is dead center in the drum. This is the simplest pattern and the most common one to use. This is also following all the rules though. It's got the node around the outside. It's actually got a second node kind of inner ring there. And then it's got two antinodes. How many nodes and antinodes does this have? By the way, this was one antinode and one node. This one's two nodes and two antinodes. What's this one? Three nodes and three antinodes. So you can create a number series of more complicated patterns that are resonant, that match the dimensions of the object and set up a nice wave inside it that appears to be a standing wave because of reflections and interference. You can actually do this in more complicated setups too. You can actually play a timpani, the big kettle drums, the boom, 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 those ones. You can actually play them by putting your hand in one spot, forcing it to be a node, and then playing a second spot, and you can actually get lopsided nodes out of this, something that really good symphonic players know how to do. You can even go to a more complicated series. By the way, hopefully if you're in chemistry, you're freaking out right now. S series, P series, oops, that should be labeled D series. I'm sorry, F series is the next one. I had a mental blip this morning. Anyway, S, P, D, F. Hope that rings a bell. If you're not in chemistry, don't freak out yet. Now, I've actually got a kiddie pool set up in my backyard, and I want to do this with my kids soon too. I saw this video, and I'm like, that's genius. Why haven't we done that yet? Where is he pushing? It's the place he's going to get moving the most, which is going to be the antinode. And what he's doing is each time he's adding a little bit of energy and therefore amplitude to the wave until the amplitude is really, really, really big. Would this work if he did it at the wrong time? No, he has to be like spot on in terms of timing to get this to work, just to drive it at the resonant frequency. I can't wait to do this with my kids. I got one of these set up in the backyard right now. It's so on my to-do list this weekend. Only problem is we put ours under our trampoline, so you can also trampoline on top of the pool. There's not a whole lot of room there, but we'll figure it out. We'll get it going. Okay, so what you get out of these resonances is called a harmonic series. You can see the simplest one, the next simplest one, the next simplest one. It's like Alice the Camel or something. There's a couple different ways to name this. You can call this harmonic 1, harmonic 2, harmonic 3, harmonic 4, harmonic blah, blah, blah. Or you can call this the fundamental, meaning the most basic one. And you can call this the first overtone, because this will also be associated with a higher pitch if you're a musician. So it'll be the second overtone, third overtone, fourth overtone. What I want you guys to notice is this is harmonic 1, this is harmonic 2, but this is the first overtone. So in the two naming systems, they're staggered. They're not quite, they don't line up, right? This is the harmonic series way to think about it. This is the alternate musical naming system used for these series, fundamental, overtone, etc. By the way, if you're a brass player, you probably have heard of this before, using overtones and fundamentals. And I'll try to get back to campus, grab some of my gear, and do a demo for you guys on my trumpet. What ends up happening is this ends up being an octave higher if you're a musician. So like da, 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 da. All right, keep going. Okay, here's the thing you might have learned about in chemistry. If you've had chemistry, if not, hold this thought. This is super important. Electrons are actually also waves, which is kind of mind-blowing. And because they're waves, the way they'll set up around the atom is based on kind of some dimensions of physical space they belong in, something to do with their frequency and wavelength. And because of that, they'll create a harmonic series. And the harmonic series in chemistry we call orbitals. And here's the simplest pattern. Here are the next most complicated patterns, the ones after that, the ones after that. We're going to go right back to the drumhead example. Here's an S series, a P series, a D series. I apologize. F is even more complicated than that. You can also have the first S, the second S, the third S, and so forth. You can keep that series going. It doesn't have to end after the third one. And so you can have like a 1s with 2 electrons in it. You can have a 2s with 2 electrons in it. You can have a 3s with 2 electrons in it. They'll each get farther and farther from the nucleus. You can also set up the electrons in more complicated patterns. And this basically is the most important thing to understand about the periodic table in chemistry. So I hope that when you guys take that, if you've already taken that, you're making connections now, that electrons are waves and they're obeying a resonance. They're following a pattern for setting up a standing wave around the nucleus of the atom based on the electron's frequency and wavelength. Mind blown, right? Okay, last up. Remember this messy graph we made? That messy graph, this one? Okay, it turns out it happens all the time. Here is the messy graph of the object called flute. And here is the messy graph, I'm going to start using the word complex waveform, of an object called a bassoon. And even if these two instruments were playing the same note, they wouldn't sound the same to you. They'd sound different. And you could tell the difference too. Like if you knew what a flute sounded like, you could always then recognize what flute sounds like. So what's cool is that this complex waveform is called a timbre. Each different object has a timbre. My own voice has a timbre. Like my own voice box has a couple resonant spots in it, as does yours. That's how you can tell the difference between your mom's yelling at you and when your dad's yelling at you. Even if they're yelling at the same pitch, they still sound very unique. It's because of this complex waveform. And you can actually break it down. This is called a fast Fourier transform. It's a whole bunch of crazy math. But you can break it down into how much of each frequency got blended together. So here's a graph of frequencies. Here's how much, the amplitude. And to make flute, you need this combo. Now what's cool is you can go tell a computer, add up together this combo of frequencies at those different amplitude mixes, and then you have what's called a synthesizer, because you've synthesized artificially the sound of a flute. Or you could switch it over. You could hit that button on that big black electronic keyboard, and you could hit that button and you could switch it over to bassoon sound. And it would be using a different combination of frequencies at a different amplitude. Regardless of which note you played, it could shift those frequencies up or down to play different notes. But as long as the combination is the same and the ratio is the same, it would still sound like bassoon. So this is how we artificially create sounds to sound like a real-life object. It's because we've mapped out the timbre of them. Timbre is the characteristics of the complex waveform that match up with an object's resonance. The way that sound or whatever else vibrates and sets up within a physical space instead of given dimensions. All right, that's pretty much it. Let's do a little bit of practice, and then we're going to come back and review this topic with some hands-on stuff on Friday. So first up, we're going to draw some harmonics in a different series. We're starting out with inside a pipe with both ends open. So here's my graph. Here's the pipe. If both ends are open, then I need an antinode and an antinode on each side. So the simplest way I could put in here to do that would be that one. That would be the first harmonic. It's the simplest thing I can put in there. A little bit more complicated. I could do that. That's the second harmonic. I'm still following the rules that at the ends I have to have antinodes. You may have noticed that there's a node here. And this one I got an additional node. That's why I'm saying it's getting more complicated. Here I had 2 antinodes and a node. Here are 3 antinodes and 2 nodes. By the way, how much of a wavelength is this? It would need to go to the middle, down back to the middle and then back up to the top to complete it, looks like I've only got half a wavelength set up in the pipe. Here, I've got one wavelength. Let's go do the next one, this harmonic series. All right, so now I've got incidents here, 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 and here. Labeling them. I've got nodes here, here, and here. And it's not perfectly evenly drawn, sorry. That's the third harmonic in the series. You could also call it the second overtone. And I've filled in 3 halves, wavelengths, within the pipe. Okay, so here's the opposite when it flips on it. So this is a pipe that's open at both ends. It's There's another possible example here. Let's jump to the second one. Let's do with only one end open. So now I'm going to have one end open and one end shut. Put that other one aside here so we can compare it later. Okay, so here's my pipe again. I've got this end open. Actually, I put this end shut. So I'm going to need a node here. And I need the other end to be open, so I could put the end in here or here. So the simplest thing I could put in would actually be that. Here's the flip side of it. And so the first one in that harmonic series, I actually only have a quarter of a wavelength because it would have to go down, come back up, go down. Okay, another option is, in that same pipe, I could do this. And what I'm missing is that much. So that's 3/4 of the whole thing. Oh, phone call, sorry. All right, next one I'm going to do. All right, there we go. And the third harmonic, I want you guys to guess real quick, don't think too hard, how much of a wavelength fit inside the pipe. This is 1/4, that's 3/4. This is a number series, so it's going to be 5/4 of a wavelength fits inside the pipe. We're going to come back and talk about this some more later. We're going to do a thing called the speed of sound investigation. I'm going to be able to figure that out. But for right now, there we go. We got, in this case, a closed end of the pipe caused a node to be there. The other end is open. We're going to have an anti-node there. And we're just trying to find, increasingly complicated harmonics, one after the other in a series, starting from the simplest one, which is also called the fundamental. So, cool. Here is our vocab review. You guys have some simple questions on Unit 6, Handout 2 to answer. There's also a Kahoot, just for some basic facts. I'll be in office hours from 2 to 3 today. Please stop by just to say hi, even if you want, and let me know if you need anything. All right, take care. Bye.